I didn't originally intend to make a second video on organic synthesis, but because organic synthesis 1 was actually filmed quite a while ago, almost 2 months ago, there are actually some things I wish to explain more that I don't think I explained very well in organic synthesis 1. And also, I want to show you two more synthesis problems that I have found recently. Not only because they're interesting, but also because I feel they are quite valuable for teaching and learning. So remember I showed you this thing in organic synthesis 1 video when I was talking about how exactly do we do a step up reaction, right? Before I get into the problems in this video, I want to consider two things, okay? Number one, how do I tell which step up reaction? Okay, because remember, I use a step up reaction in synthesis if I want to increase my number of carbons, correct? So there are two ways. What? One is nucleophilic substitution of CN, one is nucleophilic addition of CN. The way, right, is to look at this last line over here. If you have nucleophilic substitution, the number of functional groups will stay the same. Why? Because simply put, right, originally I have, let's say, this one, Cl, I go to like that, Cn. How many functional groups do I have here? I have one functional group here. I still have one functional group here. The number of functional groups has changed. On the other hand, if I have nucleophilic addition, let's say originally I had uh, a ketone like this. Okay, so this is butanedione. Yeah, correct. And then I use HCN with trace KCN-CO. I undergo nucleophilic addition. I will get something like this, right? This thing will become an OH, and on the other side of this carbon, I will have a CN. So originally, how many functional groups do I have here? I only have one, right? I have just my carbonyl. Here I have one functional group, two functional groups. So how do I tell which step up reaction to use? Okay, is you see, does the number of functional groups increase? If yes, you know that at some point I need to use nucleophilic substitution. If yes, it does increase, at some point I need to use nucleophilic addition. If no, it does not increase, then at some point I need to use nucleophilic substitution. Okay, next thing, I talked about how to add carbon, right? How do you remove carbon? There are a couple of ways to remove carbon, okay? I'm going to go through all the ways now. Number one, as you know, is oxidative cleavage. I can lose one carbon. Actually, oxidative cleavage, I can lose one or more carbons. Why? Because if I have oxidative cleavage of a terminal alkene, let's say I have built one ene, and then I have oxidative cleavage, I lose one carbon. Why? Because this carbon over here, this one here, will actually be lost as CO2. So if you recall how I do my oxidative cleavage, this thing is going to turn into a C double bond O. This thing is going to turn into a OH. And then, of course, I will plus CO2. That's oxidative cleavage of a terminal alkene. But what if I want to cleave more than one carbon? Can I do that? I can as well, right? If instead of a terminal alkene, I have something like this. Let's just put an alkene here. Then if I have oxidative cleavage here, then I will get two organic products, right? By the way, just a reminder, I've emphasized this before, CO2 usually does not count as an organic product. So when they say organic product, we usually mean two or more carbons, okay? So this one, oxidative cleavage, as we know, I'm going to get one organic product, which is going to look like this. This thing will turn into a C double bond O, this thing will turn into a OH, and then my other organic product, I look on the other side of this, okay? So originally I had something like that, right? Now this is going to turn into a C double bond O, this thing is going to turn into OH. So I get two carboxylic acids as my organic products. Okay, so this is how I cleave one carbon. I can remove multiple carbons also using oxidative cleavage. The other way to remove carbons, okay, is actually iodoform tests. Now remember, the two groups that can undergo iodoform, one of them is like this. Okay, no, I don't think I'll draw in skeletal. I have CH3 here, so it's a methyl alcohol, HOH. So it's this box structure here that I'm interested in finding. Or I can also have a positive iodoform observation if I have RC double bond O CH3. So either ethanol or some kind of methyl ketone will have this particular structure here and can form a positive observation. The iodoform test, by the way, is a redox reaction. I hope it's obvious to you why after studying it for quite some time already. And you will notice when I have, what's the RNC for iodoform test, by the way? Can you think of it? RNC for iodoform test is going to be I2AQ, NaOH-AQ, and what's the temperature? It's not here, it's warm, okay? Do not write heat. So either way, whether I have this box structure on top or this box structure on the bottom, either way what is going to happen, right, is I am actually, let me write my CH3 here so that it's easier. I'm going to put my OH here, I'm going to put my CH3 here. Then you will see what I mean, okay? I'm going to have RC, okay? Because this thing is oxidized, that's why it's a redox reaction. This thing is going to turn into a C double bond O. And then I'm going to have an O minus. So this is my carboxylate ion. Why is it a carboxylate ion? Because I have basic conditions here. That's why the carboxylic acid group is deprotonated to give me carboxylate. And here as well, this thing will still be a C double bond O, and I'm going to get O minus. But then this CH3 over here, this C over here, that's how I get my CHI3, my yellow precipitate. Of course, this is not a balanced equation. You can see your lecture notes for the balanced equation, but this is going to be my yellow PPT. And you see, it's because I have lost one carbon, that's why I get my CHI3, triiodomethane or iodoform. Understand? So that is how you lose one carbon. So oxidative cleavage, I can lose one carbon, I can lose more than one carbon. Iodoform test, I can only lose one carbon. Can you think of a third way to lose carbons, people? What's another way that you can think of to lose carbons? It starts with H, high hydrolysis. What can I hydrolyze? I can either hydrolyze an ester or I can hydrolyze an amide, correct? So how's that going to look? If I have, for example, so I'm going to look at the hydrolysis of an ester first, okay? Let us put this in blue. Let us put this in orange. So for both one, I can either have acidic hydrolysis or I can have basic hydrolysis. So let's say if I have an ester, for example, RC double bond O, this thing here is my ester linkage, COO, and then I have another R group, let's call it R prime, okay? If I have acidic hydrolysis, then it's going to be H2SO4 or dilute H2SO4 AQ and heat. So this is my acid hydrolysis. This is going to give me, this thing on the left is going to become a carboxylic acid, correct? And then this is also going to give me alcohol. Okay? If on the other hand, my this ester undergoes basic hydrolysis, I'm going to copy this over, okay? And then, let's say this thing undergoes basic hydrolysis. What's the reagents and conditions for basic hydrolysis? Instead of H2SO4, I have NaOH. Just any base will do. Actually, KOH also can, strictly speaking. So basic hydrolysis, in basic medium, will it be a carboxylic acid? No, right? Because in basic medium, this thing is going to be deprotonated. I'm going to have a carboxylate ion. And then plus an alcohol. So let's say for esters, what if I have an amide? An amide, if you recall, is similar to an ester, but instead I have this structure. So I have C double bond O, but instead of an oxygen here, I have NH and then another R group. So once again, an amide can undergo both acidic and basic hydrolysis. How? If I want to undergo acidic hydrolysis, it's still the same RNC. And then in acidic medium, once again, this is going to be a carboxylic acid. But then, what's the other thing I get from the amide? I should get an amine, right? But then, in acidic medium, I'm not going to get NH2. I'm going to get NH3 plus. This thing is going to be protonated in acidic medium. On the other hand, if I have basic hydrolysis, once again, strong base, aqueous strong base, and heat, then instead of a carboxylic acid, in basic medium, this thing will be deprotonated to give me carboxylate. And then this one, this NH2, it will just stay as NH2 lah, because it's deprotonated in basic medium. So these are my 4 conditions for hydrolysis of ester and of amide. Can? Okay, take your time to digest. I hope this is all clear. So how do you add carbon? We already know. I've covered it quite a bit. How do you remove carbon? Now I'm covering in this video, which I don't think I covered very well the last time. Oxidative cleavage, iodoform test, and hydrolysis. Can? Okay, now the 2 problems I wanted to show you. First one is this one, okay? 3-step synthesis. Can you think of how to do this? First thing that you might have noticed, right? You remember I said at the very, very start of the previous synthesis video, what has changed in the molecule? Okay? Have I gained carbon? Have I lost carbon? How many carbons in this one? Let's count, okay? Count carbons. 1, 2, 3, 4. How many carbons in this one? 也是1, 2, 3, 4. So 4 carbons. I have not gained carbon. I have not lost carbon. So I know, okay, I know that because I have not gained carbon, I have not lost carbon. Nucleophilic sub, walao, it's lagging. Okay, I have not gained carbon, I've also not lost carbon, which means that I have no nucleophilic sub, no nucleophilic add, no iodoform, no oxidative cleavage, no hydrolysis. That's a lot of things I know I don't need already. So that's a start, okay? It's a very, very good start. So think about it, right? I want to get to some kind of aldehyde. How do I go from a halogenal alkane? This is a primary halogenal alkane. How do I go from a primary RX to an aldehyde? Intuitively, you can already think, okay, I need to convert my primary RX to a primary alcohol, then primary alcohol oxidize to give me aldehyde. Okay, fine. So you are saying that before this aldehyde, I want a primary RX, right? So let's just copy it over. We can work backwards. Working backwards, in fact, I prefer to work backwards a lot more than most people do actually. Some people have greater tolerance for working backwards, some people don't. I am one of those people who has a very, very great tolerance for working backwards. But whether you have a high tolerance or low tolerance, you still need to learn and be comfortable, at least to some extent, with working backwards. Because there are some problems, right? It's actually downright unsolvable unless you force yourself to work backwards. So this one, I'm going to work backwards, copy the rest of the molecule. The other change, I don't worry yet. I worry about what I know first, okay? So I know that this one was previously a primary RX, then only I oxidize. Okay, and what's the R and C for this? This oxidation is, if I want to go from primary RX, I don't want to go all the way to carboxylic acid. I only want to stop at aldehyde. I cannot use permanganate, right? I can only use K2Cr2O7, which is a weaker oxidizing agent, with dilute H2SO4 or H2SO4 aqueous. And I explicitly need to write heats with immediate distillation. This is very important. Okay? Next, how do I get from my primary RX to my alcohol? You might be thinking nucleophilic substitution. It's just not nucleophilic substitution or CN, but it can still be a nucleophilic sub. But the question I ask you now, if I just convert this to alcohol, right? Then it will be like this. Can you have any plans to transform nothing into a tertiary alcohol in one step? No, right? So it has to be something more. And also just a quick check, right? This one is a tertiary alcohol. This one is a tertiary alcohol also. Can tertiary alcohols be oxidized, people? No, right? So because tertiary alcohols cannot be oxidized, that is why this oxidation with potassium dichromate only affects this primary alcohol here, does not affect this tertiary alcohol here. Okay, that's why my last step makes sense. Now, if I want to go from a primary halogenal alkane, I want to insert 2 alcohol groups. Can you think of any reaction in your syllabus that allows you to, in one step, insert 2 alcohol groups? Think up. Okay, I give you a clue, okay? This reaction, you learned it very early on in organic chem in J1 in alkenes. Okay, so it involves some kind of alkene. Okay, I give you the intermediate. The intermediate is going to be this alkene here. Can you think of how to go from this alkene? I add 2 alcohol groups in one go. In addition to oxidative cleavage. Is oxidative cleavage the only way to oxidize an alkene? No, right? I have mild oxidation. Because if you recall, right, if I want mild oxidation of an alkene, what I'm going to do for mild oxidation is, let's say I have this particular alkene, butene. If I oxidize it, if I oxidize it strongly using KMNO4 dilute H2SO4 and heat, okay, then I'm going to have oxidative cleavage. I'm going to cleave. And because I cleave, that's why I end up with two products like that. But what if I don't want to cleave? What if I just want this thing, okay, but I just want to mildly oxidize it, so I get rid of the alkene. And then because I oxidize, I got one oxygen here, I got one oxygen here. This is mild oxidation. Okay? So this is what is happening in this case. I have an alkene here, and then I add one OH at either end of the alkene double bond. Okay? So this is mild oxidation. In case you have forgotten, I won't be surprised if you have. The reagents and conditions for mild oxidation are as follows, okay? Because it's mild, I don't want heat, right? What's the opposite of heat? I want cold potassium permanganate. You still need to write AQ. And instead of acidification, what's the opposite of acidification? Base. So just put NaOH. Can? Can. Okay. So just remember, I want oxidation of some kind. That's why I need my MnO4. But I don't want it to be very strong. So I just put everything the opposite. Instead of heat, I put cold. Instead of acid, I put base. Okay? That's how you remember your mild oxidation versus your oxidative cleavage. Last step, how do I convert a primary RX to an alkene? This one should be very familiar to us by now. If you don't know, you go and slap yourself, okay? This is elimination, right? What's the R and C for elimination? Ethanolic KOH. Fantastic. Can? Any confusion? No confusion? Perfect. One last problem. This one. Have a think about it, okay? This one, once again, this is one of the ones, okay, is actually seriously more or less quite unsolvable unless you work backwards. So this one, I will mandate that you work backwards in this. Think about it, okay? How can I work backwards? How many functional groups do I initially have? Initially, I have one functional group, one alkene. How many functional groups do I have here? I have one alcohol, one carboxylic acids. So I got add functional groups. That's the first thing, okay? Second thing, got add carbon a lot. In my starting product, I have how many carbons? 6 carbons, right? After that, how many carbons do I have? 7 carbons. You see, 1, 2, 3, 4, 5, 6, 7. So I go from 6 carbons to 7 carbons. And not only do I increase number of carbons, I increase number of functional groups. So this is nucleophilic addition. Perfect. So I know for a fact that I want to have some kind of nucleophilic addition somewhere. I also know for a fact that because this is a step up reaction, at some point one of my steps is going to be HCN with trace KCN cold. Okay? So hang on, just let me check something. Sorry. Okay, yeah. Because some answer keys they write it as KCN with trace HCN for whatever gay reason. But yeah, I just prefer as Hwa Chong has taught me to write HCN with trace KCN. So the trace KCN acts as a catalyst because HCN is a weak acid. Okay? So what can come before a CO2H? If you think about it, right, I have a CN, right? Whether I get my CN group by nucleophilic substitution or I get it by nucleophilic addition, either way my CN only got 2 places to go. One of them is carboxylic acid, one of them is CH2 and H2. So I have a carboxylic acid, right? So maybe the thing before that, I had a cyanohydrin, like that. OH here, and CN. So in order for a CN to go to a CO2H, this has been an acidic hydrolysis, right? So what are my R and C's for acidic hydrolysis? Dilute H2SO4. Don't need to write the AQ. Heat. Okay? And then of course we are familiar with this. How do I have this nucleophilic? Hang on, I shift this up a bit. How do I get this nucleophilic addition? I have to have this nucleophilic addition to some kind of ketone, right? Because in this case, it obviously has to be a ketone before this. So in order for this to be, I had to have this 6-membered ring, and then this has to be a ketone. Then only I can get a tertiary alcohol and a cyanohydrin here. So this nucleophilic addition is going to be, as I said, HCN with trace KCN co. It's co, please don't write heat. And then, how do I get to this ketone? Okay, I give you a clue. This is a two-step synthesis from here to here. There's only one intermediate. Can you think of it? How can I get a ketone? What's the most obvious way to get a ketone? Obviously, my secondary alcohol, right? Here, that's my intermediate. So all my intermediates are done. Now I just need to figure out my R and C. So how the heck do I go from a alkene like that to a secondary alcohol like that? What I have done, right, is I have added OH to one end, but my other end I've added a H. So can you think of what? Okay, obviously this is, hopefully it's obvious to you, this is some form of electrophilic addition, right? But I electrophilic add what exactly? If I add bromine water, Br2AQ, then I'm going to add both Br and OH, but I want to add OH only. So this is going to be electrophilic addition of steam, right? What steam? Steam is gaseous water, H2OG. And you need to know that for electrophilic addition of this, you need to have concentrated phosphoric acid catalyst. And you need to say high temperature and pressure. Please memorize this RNC. A lot of people, by the time they get to the end of organic chem, they forget everything they learned in alkanes, alkenes, arenes already. Please get your J1 organic chemistry correct. Okay? All these things you knew in J1, you should continue to know in J2. Just because you have learned more things doesn't mean you can forget things, okay? So just remember that you need to know this RNC for electrophilic addition of steam. And then lastly, obviously, how do I get from secondary alcohol to ketone? This one, whether you use KMNO4 or K2Cr2O7, I don't care, but I just prefer to use KMNO4. And remember, the only times in which you cannot use KMNO4 is if you deliberately want a slightly milder oxidation. So for example, if I want my distillation with K2Cr2O7 to form an aldehyde, or if I'm purposely trying to avoid an oxidative cleavage or a side chain oxidation. So if I want to oxidize, but then there's a alkyl benzene that I don't want to be oxidized, like let's say I have an alkyl benzene and another functional group. I want that other functional group to be oxidized, but I don't want my alkyl benzene to turn into benzoic acid. I cannot use permanganate, I have to use dibromate. Likewise, if I have another functional group that I want to oxidize, but I have an alkene that I don't want to touch, then I have to pick an oxidizing agent that doesn't touch an alkene, i.e. have to pick dichromate. Can? So I think that's it for organic synthesis. I showed you 2 new problems. Hopefully you have learned something about hydrolysis, about iodoform tests, and yeah, okay. Actually, come to think of it, did I mention iodoform test in the previous video? I think I might have. Yeah, I definitely have. So sorry for repeating myself a bit, but I hope I mean I've learned something from revisiting synthesis and recording this. I hope you've learned something as well. Thank you and bye bye.